In this video, we're going to look at section 12.2, vectors. The term vector is used in a lot of different situations. Quite often in science it's indicated quantity. So you're going to see a vector drawn as a line in a graph, but it actually has a lot more meaning than that. Vectors also have an arrows on it that directs the direction of that vector. The arrow represents the magnitude of the vector and also points in the direction of the vector. So we denote a vector by printing the letter bold and putting an arrow over it, detecting the direction of it. For instance, we have two vectors drawn on the paper below. We have AB, which is vector V. Now that's known as a displacement vector, as an initial point of A, that's where it starts, and a terminal point where it ends of B. You also see that U, vector U, CD, is the exact same direction and the exact same length. So we can say that those two vectors are equivalent. So we can say U equals V. It is very important to notice that they're the same length and the same direction. If it went a different direction, they would not be equivalent. A zero vector, so a vector that has no length, is the only one that we actually can decide it does not have a specific direction because it doesn't have any length. Next thing we're going to look at is combining vectors. So if we start with vectors u and v, as we see here, and we place v at the terminal point of u, we actually get a new vector. So we actually call this vector addition. So the sum of uv is going to produce a new vector, as you can see here, and that's u plus v. So that's known as the triangle law. When you look at those two vectors, it doesn't actually matter the direction or where they're located. As long as the direction's the same and the length is the same, they're the same vector. So as you can see here, we actually put them up on top and we get to the exact same point. So they call this the parallelogram law, in essence, because we have those two sides are parallel to each other. So we can actually have them both there, and we're still going to get to the exact same point in my parallelogram. So u plus v equals v plus u. So the rules of addition still hold true even with vectors. The next thing we want to look at is scalar multiplication with vectors. So if I take a vector and I multiply it by some constant, that vector is going to be parallel to the other vectors, but it's going to have a different length. So it's not going to be equal to the other vector, but it is going to be parallel and have a different length. So we actually can multiply by a negative value as well. So if we look here, we have v, we have 2v, half v is half that, and then we have the negative ones. The negative ones are also parallel to the original vector, except they go the opposite direction. So they're going to go down instead of up. Now, if we combine scalar multiplication of vectors and addition, that's how we're going to get the subtraction of vectors. So the difference of u and v is really the same thing as u plus negative v. So if we look at that, we have u and v. So negative v is going this way, so my u minus v is going to go down to that point there. So you can have subtraction of vectors as well. The next thing we're going to look at is the components of a vector. When we're looking at a vector, sometimes it's best to look at it as a coordinate system. So we want to be able to do those calculations on it. The two pieces of a vector that I need to know is its magnitude and its direction. So we can take, as we looked in the last part, a vector that's moved and shift it, and they're going to be equivalent. So if I focus them back down at the origin and look at where they're coming off the origin, it makes all of my calculations a lot easier, but I will still have the same vector and I'll still be able to do those calculations on them. So we're going to call these the components. So if you notice, they look very similar to a point. However, there's those notation around them is not a parenthesis. It's that triangled off parenthesis. So A in a 2-coordinate or a 2D plane, it would be A1 and A2. If you look at it in a 3D plane, it's the same thing. We just add the third coordinate value to it. So if we look at figure 12, all those vectors are equivalent. The one that's going to help me the most, the one that's going to make the easiest calculations, is the one that's in the middle, and that's P of going to 3 and 2. So this way, I don't need to look at all those other things. I can be able to do the calculations with my starting point being at 0. The first thing we have to do, though, is we have to be able to get that and figure out what that value is first. So if I take a vector that's been shifted off, I know that something is being added to each value for that x, the y, and the z. I just need to figure out what that value is. And that's where I'm looking at the x plus a1, y plus a2, and z plus a3. The a1, a2, and a3 are actually going to be the values that is going to be my position of the vector that I'm going to use to calculate it out. All we have to do to figure that out is subtract the starting point and the ending point. We're just looking at the change. It's no different than we're finding the slope. We're looking for a change in x, change in y, and then change in z if we're looking at it in 3 dimensions. Those values are going to give me a1, a2, and a3. So if I look at these 2 points as an initial point of 2, -3, and 4, and a terminal point of -2, 1, and 1. So I'm going to say 2 minus 2, 1 minus a -3, and 1 minus 4. So my positional vector is -4, 4, and -3. The next part that we have to look at is the magnitude or the length of the vector. To do this, I'm just going to do the distance formula. But we need to figure out what the a1, the a2, and the a3 are first. So by doing that, that saves me the hassle of doing the x1 minus x2 inside the distance formula. Since I've already done that part to figure out the endpoint, now I just have to figure out my magnitude. So I'm just going to do a squared plus a1 squared plus a2 squared in the 2-dimensional one, or add in the a3 squared in the 3-dimensional one, and do the square root. It's a simple distance formula. By doing that, I now have the position and the magnitude of that vector. So this allows me to do all the other calculations and stuff with it a lot simpler. So I can do addition. A plus b is just adding the 2 pieces together. I can do subtraction, that's just subtracting them. And I can do multiplication, that's just multiplying every term by a single value. So if we look here, the properties of the vectors, these are very similar to ones that we've seen before when we're just doing addition, subtraction, and multiplication. Is we have a plus b equals b plus a. We can shift the things around and add up in different values. Adding 0 doesn't change it. Doing the opposite of it, the negative version, cancels it out. Multiplying, we can do distribution. And if there's multiples, I can do the multiplication in any direction, and multiplying it by 1 is going to give me the exact same thing I started with. Now, there are 3 vectors that play a very important role: I, j, and k. These are known as the basis vectors. These vectors have a length of 1 and are on the x, y, and z axis. By having these values there, we can actually start to come up with equations for our vectors. So those vectors allow me to take the a value. So a1 is going to be times the 1, 0, and 1. a2 is going to be times the 1 in the middle, because that's going to give me my y. And a3 is going to be times the 1 in the z. Now, since I know those vectors are straight, I call those I, j, and k. That allows me to express my vector in terms of a formula that I can then do some calculations for. So example 1, -2, and 6 is I minus 2j plus 6k. And that would give me the same vector, but now it's in an equation that I can do some calculations on. And we can start looking for the coefficients of those values in our work.